In today's fast-paced and highly competitive global market, manufacturers face numerous challenges. They need to optimize production processes, reduce costs, improve quality, and ensure timely delivery to meet customer demands. Until now, most of the companies used lean manufacturing principles to pursue productivity improvements. This led to lean principles being part of the DNA of many business. However, classical lean principles are losing some of their edge. As a matter of fact, the very success of the lean approach means that further improvements are marginal and very hard to achieve. Even if lean principles will remain fundamental, there is a need of enhancing such principles. The adoption of newer technologies, advancements in data collection, together with automation and artificial intelligence, will enable companies to continuously improve their business. A Google Trend Score analysis, graph on the top, shows that Industry 4.0 is expecting to become the new productive imperative, and is expected to lead operations to the next S-curve of productivity. This is also confirmed by the fact that 68% of the companies that took part to the McKinsey Global Manufacturing Survey see Industry 4.0 as a top strategic priority. However, the survey also shows that only 30% of the companies are capturing value from deploying Industry 4.0 solutions at scale. Most of the companies are still in the piloting phase, as shown in the graph on the bottom. Given the motivation, the overall problem is well summarized in the following sentences. The problem today is not product innovation and/or servitization, where the greatest potential is building the machine that makes the machine. Factory today needs to be agile, however agility of a company is limited by its least agile building block. All the layers of the company needs to be agile. To improve agility, Industry 4.0 solutions are the answer. However, very few companies were able to integrate these solutions at scale. In order to frame this work, it is necessary to understand the anatomy of a manufacturing company. For doing that, the standard ANSI ISA 95/IEC 62264 is used to show the functional hierarchical organization of the manufacturing enterprise, and the ISA 88 together with the ISA 95 for showing the physical hierarchy. Here, optimization and overall improvements in productivity can happen in several and distinct levels of the enterprise. However, the focus of the PhD is to deliver agility to the business by acting on the manufacturing operating processes. This means that the level 3 of the ISA 95 model is the target for the research. Looking at the manufacturing system in a more concrete way, the research is set on this path, moving from the current situation, where the system is characterized by high automation, low connection between the levels, and operational technology deployed until level 3. To an integrated automation stack, where OT is smashed to the only level where it makes sense, while the rest of the system shares the same software infrastructure to support a software platform strongly based on cloud-native technologies. Finally, cloud-native manufacturing execution systems represent a pivotal shift in how manufacturers can optimize their operations. With unprecedented flexibility, connectivity, analytics, security, and cost-effectiveness, these systems empower companies to achieve operational excellence and drive innovation. With this in mind, the following research question has been formulated. Do cloud-native principles promote the creation of Industry 4.0 compliant advanced MES to support manufacturing operations management? And the following hypothesis has been set for guiding the research. Cloud-native principles lead to the design and development of fully managed, evolvable, resilient, available, and designed for automation software solutions constituted by modular, easy-to-deploy small capabilities or functionalities. These capabilities or functionalities are distributed across a network of interconnected hardware and software components. Moreover, to narrow the focus of the research, the following sub-questions have been formulated. RQ.1. What are the recurring problems and related solutions in designing and structuring Industry 4.0 compliant data-driven solutions? RQ.2. How to properly describe and model a physical asset to be connected in digital world to enhance transparency, end-to-end visibility, traceability and real-time data availability. RQ.3. What are the most promising cloud-native technologies and tools to use when designing and structuring MES for manufacturing operations management? RQ.4. How to adopt modern software engineering practices, pioneered by IT tech companies, to enable agile software development and delivery. Here, there is the schedule and envisioned execution plan of the PhD. The following milestones have been identified. 1. Background review and problem characterization. This will trigger the implementation of an early prototype to showcase the idea behind the research. 2. Alpha version of the prototype ready. 3. Literature review and state-of-the-art analysis. This will trigger the beta implementation of the early prototype. 4. Beta version of the prototype ready. 5. Implementation of the full prototype and testing in relevant industrial scenarios. The proposed research is building up on results of previous projects, from European research programs, where the author has had an active role, namely Mantis and Prophesy. Moreover, the research proposed in this presentation will also gather input and will contribute to ongoing projects, such as BD4 Energy, Circular Twain, Ready, and Modular. The presented roadmap, also, highlights how each project contributes to the research. The one-page abstract shows the main objective of the research: to create a connected ecosystem where various entities, within a manufacturing or industrial environment, can communicate and exchange data seamlessly. The entities involved can include physical products, machinery, equipment, and human operators. The foundation of this concept lies in the use of asset administration shells. An AAS is a digital representation or virtual counterpart of a physical entity or asset. It encapsulates important information about the asset, such as its identity, properties, capabilities, and behavior. AASs serve as a standardized and structured way of exchanging data and interacting with assets in the ecosystem. A cloud-native manufacturing execution system plays a vital role in managing the entire ecosystem. The MES plays the role of operating system while managing resource allocation, discoverability, monitoring, scalability of data collection and provisioning, as well as rolling updates and continuous deployment. To do that, cloud-native technologies will be used. Overall, the solution is leveraging Docker and Kubernetes together to create a cloud-native MES architecture that is highly scalable, portable, and resilient.